In this video, we're going to talk about one-sided limits. If you see here, a one-sided limit is a limit that has just one side. So as you approach x from the left side or the right side. So if you think about approaching from the left to right, think about yourself walking down a street. So if you have to approach a grocery store, you're going to approach the grocery store from the left, or you're going to approach the grocery store from the right. So if the grocery store was the x value 0, let's say here's your little grocery store that you want to go to. You're going to approach the grocery store from the left side, would be you're coming from the left side. If I'm approaching the grocery store from the right side, I'm moving in this direction toward x is equal to 0. Same thing happens here. As you approach x is equal to 0 from the left, you're moving toward x is equal to 0, but you're coming from the left side. If I'm approaching x is equal to 0 from the right side, I'm coming toward x equal to 0 from the right side. Okay, so I find it helpful to imagine that you yourself are on the graph and you're walking and you're approaching it, the point itself, from that direction, left to right. So let's look at this example here. The limit is x approaches 0 from the left side. Now notice the notation. If you're approaching from the left side, there's this minus sign that becomes a upper script. It's not an exponent, but it's just placed up on the top. That tells you that you're approaching it from the left. So right here, approach x is equal to 0 from the left. Your y value is getting very, very close to the number -1. Similarly, as you approach x is equal to 0, you're walking down that path. You're walking, your y value is getting close to the number 1. What usually gets confusing here is students aren't sure, well, what am I looking at, the x value or the y value? Remember, the limit is going to be a y value. So the limit equals some y value. This here is your x value. So as x gets close to 0, what's the y value getting close to? As x gets close to 0, what's the y value getting close to? Okay. Now what happens is sometimes the limit on the left doesn't equal the limit on the right, which is exactly what happens here. They're different y values. And you can tell by the picture, they're not meeting at the same place. So the limits are not the same on the left and the right. So this is a really important rule. A limit as a whole, all the limits that we've been talking about in the previous videos have said that there's been a limit. Well, the only time that there's a limit is if both the limit on the left is equal to the limit on the right. Notice quickly, I just forgot to say this part. See how this had a negative sign? If you're pushing from the right, the upper script is a plus sign. So here is this definition. It's extremely important. So a limit exists if and only if the limit as x approaches a from the left, see a minus sign, of f of x is equal to the limit as x approaches a from the right of f of x. So in order for there to be a limit, the left and right limit has to be the same. Most of the time you'll see this axed as a piecewise function or as a graphical example. So they'll give you a picture and they'll say, okay, what's the limit as x approaches some value left, right, etc. Or a piecewise function, because then you'll have all these different pieces that make up the graph. So be comfortable with knowing that there can be a left-sided limit, a right-side limit, and if they're just talking about limit, notice that if they just say the limit as x approaches 0 of f of x, no plus or minus sign, and the plus or minus sign being on the top part. If there's no plus or minus sign, they're talking about the limit as a whole, there is none. So this would be does not exist. D and E doesn't exist. Earlier, we had looked at this exact same example, and we had said that there was no limit. So if you look here again, we're now going to introduce this idea that, yeah, there isn't a limit, but we can notate it a little differently. So we call this infinite limits. So if we're looking at the function 1 over x squared, this would be the graph that represents that function. And we wanted the limit as x approaches 0. Notice that as x approaches 0 from both the left side and the right side, the y values from both sides are approaching infinity. So if they're both approaching the same area, same vicinity, same infinitely large value of y, we can say that the limit is infinity. Now, this still means there is no exact letter L, like no number L, so there is no, the limit still doesn't exist, but we can notate it as infinity, so that gives you an essence of where the graph is going, or the direction and the area of those, as x is close to 0, where's the y moving towards? And you can see that by using the notation infinity. Now let's look at this example. What if f of x is equal to 1 over x? And this is the graph of 1 over x. What would be the limit as x approaches 0 of 1 over x? Now go back to the concept of one-sided limits. So in order for the limit to exist at 0, both the left and the right side have to be approaching the same number, or both have to be approaching the same infinity in order for it to have the notation of infinity or a number. So let's look at the limit as x approaches 0 from the left side. As x approaches 0 from the left side, the y value is getting close to negative infinity. As the limit as x approaches 0 from the right side is approaching positive infinity. They're not the same infinities. So in the previous example, we were to use infinity as where the limit was moving towards, even though it didn't exist, but we can't do that here. So the limit as x approaches 0 of 1 over x does not exist. You can't put infinity or positive infinity because it's not the same infinity value, infinity notation. The next type of examples we're going to look at are limits at infinity, which means as x approaches infinity, not the result of the limit being infinity. So this is a little different. So what this means is x is approaching, normally look at the limit as x approaches some number. But now we're going to look at what happens as x gets really large, or what happens when x gets really small. Really large being infinity, really small being negative infinity. So we're going to look at an example, f of x equals 1 over x. So that's the graph that we have drawn here. So if you look at f of x is equal to 1 over x, and then think about the limit as x approaches infinity. So that means as x gets very large. So right here's your x value. As x gets very large, this y value, remember the y value, is getting close to 0, or getting close to the x-axis. You see that? The y value as x gets really large is getting really, really, really close to that x-axis. Similarly, as x approaches negative infinity, so that means super small, the y value is getting really, 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 really close to the x-axis again. And the x-axis has the value y is equal to 0. So be aware if the limit question is asking you as x approaches a number or if x approaches infinity. Because if it approaches infinity, you're looking at the example at the extremes of the graph. This next rule is a very important rule for limits at infinity. You'll find that you'll use this rule quite often when your x value limits as x approaches infinity or negative infinity. Just be careful that this is only true when x approaches infinity or negative infinity, not true when it's x approaches a number. So firstly, the limit as x approaches infinity of 1 over x to the p, where p is some number. We could say it's any really rational number that we have, will be 0. Same thing, the limit as x approaches negative infinity of 1 over x to the p is also 0. And that's evident in the example that we saw before. Now, here's a really important rule, and it seems a little wordy, and it will make sense when we do an example, but this also has merit in itself, so make sure you can comprehend what we're going to say here. So limits at infinity for rational functions is the name of the rule that we're looking at. If f of x is a rational function, and a sub n x to the n and b sub m x sub m are the terms in the numerator and the denominator respectively. So if we stop there, these are both terms. This a sub n x sub n is a term in the numerator. B to the m x sub m is a term in the denominator. The a to the n is the coefficient of the x term. The b to the m is the coefficient of the x to the m term. Okay. Now, not only are they terms in numerator and denominator respectively, they have the greatest powers of x in both numerator and denominator, which means this x to the n, that n should have been the largest exponent value of x in the numerator. And the same thing, that x to the m should have been the highest power of x in the denominator. So what you can say then, if this f of x is some long rational function and it has the x, a to the n, x to the n in the numerator, b to the m, x to the m in the denominator, and other terms as well, but those being the ones that have the highest powers of x, you can then just look at them to get your solution for the limit as x approaches infinity, which means the limit as x approaches infinity would then be a to the n, x to the n, b to the m, x to the m. So you would just look at that and then simplify. Let's work on some examples of the rule that we just stated before for limits at infinity. So let's look at number 1. The limit as x approaches negative infinity of x to the 4th minus 3x all over 5 minus 2x. So if x is approaching positive infinity or negative infinity, you can look at the highest term of the power of x in the numerator as well in the denominator. So if we see in the numerator here, the highest power of x is present in x to the 4th, and in the denominator, it's the minus 2x. Make sure you keep the sign in front of the term as well. So this means we can look at the limit as x approaches negative infinity of x to the 4th all over negative 2x. And then you simplify it. Now you may be able to use the other property, the limit as x approaches infinity or negative infinity of 1 over x to the p is 0, but you may not be able to use that. So let's see what we get here when we simplify this term, because that's what we want to do as well. So we get the limit as x approaches negative infinity of negative x to the 3rd all over 2. Why is it the negative? I just brought the negative up. The x goes into x to the 4th, you get x to the 3rd, and that's our solution here. Now, as x approaches negative infinity, you can think graphically what might happen here, what x to the 3rd looks like, and what x to the 3rd, negative x to the 3rd looks like. Negative x to the 3rd has the form of that there. So as x approaches negative infinity, it's approaching positive infinity. Similarly, we would do the same thing in example 2. Example 2 has the limit as x approaches infinity of this same function from number 1, only difference is where it's approaching. So the same writing will happen. The only difference is that it's going to be the limit as x approaches positive infinity of negative x to the 3rd all over 2. And then if you think graphically, as x approaches infinity, it's moving downwards, so it's being negative infinity. Let's look at example 3. X approaches infinity of x squared minus 1 all over 7 minus 2x plus 8x squared. So we get the highest power in the numerator, highest power in the denominator, x squared all over 8x squared, and 1 over 8 is your answer. Nothing more that you need to do. Okay, because then you could say the limit as x approaches infinity of 1 over 8 is just 1 over 8. Similarly, let's look at number 4. Number 4, you want to expand that denominator because you need to see a highest power that's present in the denominator. So we're going to get x all over. When you expand that, please make sure you FOIL. So you get 9x squared minus 6x plus 1, highest power. So this becomes the limit as x approaches negative infinity of x all over 9x squared. You can simplify that, so that is the limit as x approaches negative infinity of 1 over 9x, and then you use the rule from before. The limit as x approaches infinity or negative infinity of 1 over x to the p is 0. So you have that x in that denominator. So therefore this result is the number 0. It's a really important rule, and you want to make sure you're comfortable with that one as well.